Multiverses are everywhere. Movies, popular science articles, philosophical debates, Family Guy episodes. At one time or another, we've all been invited to imagine copies of ourselves running around in some other dimension, living out a life almost but not quite identical to our own. But why do people think multiverses exist in the first place? As it happens, I spent the first half of my time in grad school trying to figure out the answer to this question, and the second half trying to figure out how to explain it to people who don't have a physics degree. So without further delay, here's a 100% math-free walkthrough of the multiverse theory known as many worlds quantum mechanics. Quantum mechanics, a dirty little secret physicists like pictures. To be honest, 80% of quantum mechanics work just involves drawing a series of pictures that show how something we're interested in changes over time. But physicists have fragile egos and don't want you to know that. So they put special boxes, called kets, that look like this, around the pictures to make themselves think that they're doing something more complicated than they actually are. All the ket means is that you're talking about the quantum state of whatever is drawn inside. And quantum state is just fancy talk for state, which is just fancy talk for the way a thing is. Example. The thing to keep in mind is that the main difference between some idiot drawing stick figures and a quantum theorist is the use of the ket in the image on the right. All the ket means is that we're talking about the object that we've drawn in the context of quantum mechanics. To blend in, we'll use this fancy ket notation in what follows. But just keep in mind that what we're really doing is just drawing pictures of stuff. Meet the electron. In order to understand why there are probably copies of you running around in countless parallel universes, we'll have to start small. You've probably heard of electrons. Electrons are tiny, subatomic particles. For our purposes, you can think of an electron as a very, very small sphere. Spheres can spin clockwise or counterclockwise. And electrons can too. Here's what an electron might look like when drawn using our ket notation. The only weird thing about quantum mechanics. There's only one weird thing about quantum mechanics. Like a baseball, electrons can spin clockwise or counterclockwise. But quantum mechanics says that tiny particles like electrons have a superpower. They can also spin clockwise and counterclockwise at the same time. Holy shit. To imagine how this works, it helps to think about colors. If clockwise is white, and counterclockwise is black, then what I'm saying is that electrons can be gray. This is obviously a confusing concept for most of us to grasp, since we've never seen anything spin in two directions at once. But the math says that's exactly what's going on. Let's see how we can draw this situation out using our ket notation. We'll indicate that our electron is doing two things at once by adding together its two kets using a plus sign. According to quantum mechanics, these gray particles are everywhere, spinning in two directions at the same time. But hold on, you say, if the world is full of weird objects that are spinning clockwise and counterclockwise at the same time, why have I never in my entire life seen that happen? That excellent question is at the heart of what has become known as the quantum measurement paradox. And the answer will lead us straight to the multiverse. Telling stories with kets. Before we can introduce the multiverse, we need to take a second and talk about how to tell stories with kets. Imagine you had an electron in a closed box. There's a special detector next to the electron that will go click if the electron is spinning clockwise, and won't do anything if it's spinning counterclockwise. If this spin detector clicks, it will send a signal to a gun, which will then fire and kill a cat also in the box. Let's draw out this scenario with our ket notation. If our electron is spinning clockwise, here's how things will look before the detector has been turned on. A minute later, we turn on the detector. Because the electron is spinning clockwise, the detector goes click. We'll indicate that with a little check mark. The detector now sends its signal to the gun, which goes off a fraction of a second later, at which point our box looks like this. The bullet flies through the air, and a moment later, it reaches our cat, which becomes the sad victim of our experiment. Compared to this, the case where the electron is spinning in the other direction is very straightforward. Because the electron is spinning the wrong way, it won't trigger the detector, and nothing will happen. These two stories, one where the cat lives, and one where it dies, seem to make perfect sense so far. But what if our electron doesn't simply start off spinning one way or the other, but instead spins in both directions at the same time? 2 words, zombie cat. Quantum zombie cats. Let's tell a new story. This time, our electron starts in its simultaneous clockwise and counterclockwise spinning state. Here's what this will look like when drawn using kets. Now the million-dollar question, what happens when we turn our electron spin detector? Will it click, or not click? According to quantum mechanics, it does both. Part of it will see a clockwise spin, and part of it will see a counterclockwise spin. It's almost as if the detector is being split in two by our electron. Again, using kets. Notice that we have two different mini-stories forming inside the red brackets. In one, the electron was spinning clockwise and the detector clicked, and in the other, the electron was spinning counterclockwise and the detector didn't budge. Next, we wait for the signal to propagate from the detector to the gun. Will the gun go off, or will the bullet stay in the chamber? The answer is the same as for the detector, it will do both. The gun will be split in two, one version of it having gone off, the other never having fired. Which brings us to our cat. By now, you can probably guess what its fate will be. The cat, just like the spin detector and the gun, will be split in two, one version will be killed by the bullet, and the other will go on to do great cat things. Here's the final state of everything in our box. Notice that we now have two fully independent stories to tell about the contents of the box. In one, the electron spin was clockwise, the gun went off and the cat died. In the other, the spin was counterclockwise, the gun didn't go off and the cat lived. Both are true. Neither is more true than the other. They coexist inside the box. Is the electron spinning clockwise or counterclockwise? Both. Has the detector clicked or not? Both. Is the cat alive or dead? Both. #zombie cat quantum consciousness. Okay, so you're skeptical of the story I just told you. You've never seen a half-dead, half-living cat. You might even want to say, well, clearly quantum mechanics doesn't work because I've never seen a zombie cat, so let's throw out the whole thing. But the problem is that quantum mechanics makes the best predictions of any physical theory of the universe we've ever had, like, literally ever. So we can't throw the baby out with the bathwater. Somehow, we're going to have to explain why quantum mechanics says there should be zombie cats, when no one has ever seen one. And that's what a guy called Niels Bohr wanted to figure out. He came up with the first real attempt at explaining the zombie cat problem. To paraphrase, Bohr was like, I've never seen a zombie cat, but the math says it's there. So there must be something special about me, that forces the cat to choose its state, either dead or alive, when I look at it. When I look at it, the cat must be forced to collapse out of its simultaneous alive-dead state and becomes either alive or dead, not both. He probably said it in Danish, but that was basically the gist. Here's what Bohr was suggesting. Although this does explain why we never see zombie cats, many people today see it as an unnecessary bit of magic to introduce into our laws of nature. At the time though, the physics community was pretty freaked out about the zombie cat problem, and most jumped on Bohr's bandwagon. But Bohr's explanation had some holes in it that no one could quite plug. What makes humans so special that they can force a quantum system, like our electron, detector, gun, cat system, to collapse into a single, well-defined state, like dead, or alive? Does the cat have the power to collapse the state of the electron, detector, gun combination? Would a monkey? How about the gun or the detector? Why can't they collapse the state of the electron? Some people started throwing around some pretty new-agey terms in response to one. It's human consciousness that collapses the zombie cat into its alive or dead state. The act of observation affects the quantum system, and induces it to collapse. Leaving aside the fact that it's totally unclear what anyone might mean by consciousness, or observer, we still have problems 2 and 3 to deal with. So how do we get mind magic out of the equation? One word. The multiverse. Luckily for us, the story doesn't end here. In the 1950s, a bloke called Hugh Everett III came up with an alternative way of explaining why we don't see zombie cats all around us. Everett said, listen up, you dickheads. What makes you think you're so much better than a freaking cat? You're not. You're just a bum with a chalkboard. Absolutely pathetic. Also, your fly is undone. Dumbass. It's not a direct quote, but hey, if you wanted historical accuracy, you'd go to Wikipedia. What Everett was getting at was that we really shouldn't be thinking of humans or observers as being special in any way. Instead, he suggested thinking of ourselves as quantum objects, that we could put in a ket, just like the cat, the gun and the detector. Let's see how that would play out. We'll take our zombie cat box, and explicitly add the experimenter, observer as another part of our system, in a ket like everything else. Before the experimenter looks inside the box, here's how our system will look. Now he looks inside. Just like the cat, the gun, and the detector, he too is split into two distinct copies of himself. Now imagine asking the experimenter, both versions of him, what the result of the experiment was. Was the cat dead? One version will give a definite yes, and the other a definite no. Did you see the cat alive and dead simultaneously? They both give the obvious answer, of course not. What a stupid question. In each case, the experimenter only ever sees one outcome: the cat is either alive or dead, but never both, even though the laws of quantum mechanics say that both versions of the cat do exist. The experimenter just doesn't notice because he's stuck in one of these two timelines, unable to see the other one. And that was Everett's point. The reason we've never seen zombie cats or half-fired, half-not-fired guns is because the moment we look at these objects, we ourselves are split into multiple timelines, where different versions of us see different, but well-defined, outcomes. Until now, I've been referring to the two groups of cats, one where the cat is alive, and the other where the cat is dead, as stories, or timelines, but another word you might just as well use is universe. That's because everything about the alive and dead timelines will begin to change dramatically from this point on. For example, the experimenter who sees the dead cat might be so saddened that he ends up quitting his job, and never inventing a key technology that would otherwise have been used by millions of people. It's interesting to note that this giant difference between the alive and dead universes all arose from the spin of a single tiny electron. And because electrons and other particles are leading parallel lives all around us, our multiverse is constantly splitting, spawning off new timelines or universes with every possible interaction outcome.